Hello once again. We're starting in section 4.3 today, in which we're going to start a series of sections in which we're going to start proving that triangles are congruent to one another by various methods. All right, you've seen how to prove or how to know that two figures are congruent. Now we're just going to focus on triangles in particular and look at maybe shorter ways of accomplishing the same thing that we did in the last section. Your goal in this video is that you're going to use the SSS, also known as the side-side-side congruence postulate, to determine whether two triangles are congruent to one another. Now, I want to start off by explaining a simple concept here of what we're trying to accomplish over the next several sections. And I want you to look at this picture of a triangle that I've got right here in order to explain that principle to you. We know that two triangles are congruent if all the sides of the triangles are congruent to one another and all the corresponding angles of the two triangles are congruent to one another. But it turns out that you can have two congruent triangles that you know are congruent without having to measure every pair of sides and every pair of angles. And I want to demonstrate to you that it actually, instead of proving that all three pairs of sides and all three pairs of angles are congruent, you can take certain sets of three measurements in order to show the two triangles are congruent. What I would like to do is show you in this case how I could actually create another triangle that's congruent to this triangle that you see right here by just copying the side lengths of the triangle and not even worrying about the angle measures. Alright, so you see a segment AB, a segment BC, and a segment AC. I want to copy all three of those distances and show you that it's going to create a triangle that's congruent to this one. Alright, let me place a point somewhere. And what I want to do first is I want to copy this distance AB. That's just the one I'm choosing to do. And in order to copy that distance AB, I can kind of use slope in a sense. I'm not using slope in its simplest form, but I am using slope nonetheless. If I look at the distance from A to B, well, I would go up 2 units and right 4 units in order to make that distance, wouldn't I? So, what I can do in order to copy that distance is I can move 2 units in one direction. Doesn't have to be the same direction as a moment ago. And then I can move 4 units in another direction. And it'd be guaranteed that the distance that I just found then is congruent to that first distance that I made. So this segment DE would be congruent to this distance, or equal to that distance from A to B. Alright, next thing I'm going to do is I'm going to copy the distance from B to C, and I'm going to make that from point E to some point F over here. I'm going to use the same basic strategy to copy that distance. Notice that from point B to point C, if I go right 3 units and then down to 6 units, well, that creates the hypotenuse of that triangle that I created is segment BC. So I'm going to go 3 units in one direction and 6 units in another direction from point E to try to create another segment that's congruent to segment BC, like this. You see, I decided to go up 3 and right 6 units. And that gave me this segment EF, which is definitely the same length as segment BC. Alright, and then I'll finally go ahead and connect points D and F. Now, I did something here that I didn't describe to you, but I also ensured that the distance from D to F was the same as the distance from A to C, and I'll demonstrate that to you right now. Although it is less obvious, you see here that I made, going from point A to C, you've got a triangle that's 4 units and 7 units. Whereas here from D to F, I've got a triangle that's 1 unit by 8 units, at least for the two sides that I measured. However, if you use a distance formula or the Pythagorean theorem to find out what the length DF is compared to the length AC, you're going to find that they both are the square root of 65. Now I'm going to go ahead and write the distance for the other sides just to make my point here easier to prove. So you see that the 3 side lengths for this triangle are the same as the 3 side lengths for this triangle. Now, turns out that if you just know that all 3 side lengths are congruent for those 2 pairs of triangles, that the triangles automatically are congruent. I don't have a protractor to use along with the app that I'm using right here, But you could grab your protractor and place it on your screen, and you can measure the angles A, B, and C, compare them with the angles D, E, and F, and you'd see that you'd have 3 congruent angles along with these 3 congruent sides. Now I can do this much for you. If you use slopes, you could show that that's a right angle right there, and you could show that this is a right angle over here as well. Then you just have to be able to show that the other 2 pairs of angles are congruent to one another. All you have to do to make 2 triangles that are congruent, though, is copy the 3 side lengths, and it automatically makes the angle measures congruent to one another. And triangles are the only shape that works with. If you copy the side lengths of a square, for instance, all of these side lengths are 5, and all of these side lengths are 5, but that didn't make the angle measures congruent, did it? But in triangles, if you copy all the side lengths, you're also going to get equal angle measures all the time. And so that leads us into what's called the side-side-side congruence postulate, which is a postulate that basically tells you that if all 3 sides of one triangle are congruent to the corresponding sides on another triangle, that the 2 triangles automatically have to be congruent. In other words, those 3 sides make all the sides and angles congruent to one another. Now let me write this out using the vertices that I've labeled on our 2 triangles. Alright, if we know that segment PQ is congruent to segment WX, segment QR is congruent to segment XY, and segment PR is congruent to segment WY, then that automatically makes these 2 triangles congruent to one another. We don't even have to know what the angles are. They are congruent to one another. And whenever you use the fact that all 3 sides of one triangle are congruent to all 3 sides of another triangle in order to prove that the triangles are congruent, you're using the SSS postulate. And so I wrote by the side-side-side congruence postulate. Excellent. Let's see how we can use the side-side-side congruence postulate. What I'd like us to do in these next couple of pictures is to decide whether the congruent statement that is given to you is true and explain your reasoning. And you see the congruent statement right there. I'm going to highlight it because it's kind of close to the picture. So is triangle BCA congruent to triangle DAC? And we're going to explain our reasoning. Well, what we're going to try to do is determine, do they have 3 pairs of congruent sides? And that's going to be pretty easy for us, actually, to determine if they do have 3 pairs of congruent sides. The answer is going to be yes to this. You can see that it's given to you that segment A, B, and segment CD are congruent, as well as segment BC is congruent to segment DA. Let me write a little bit of this. I already said our answer would be yes. And you can see that idea expressed right here. Well, what about the 3rd pair of sides? Well, the 3rd pair of sides of these 2 triangles happens to be the exact same segment. This distance from A to C is the 3rd side of each of those triangles. And there's no way the distance from A to C is different in this top triangle than it is in the bottom triangle. They have to be congruent to one another. Now I'll explain why I wrote AC here and CA there in a moment, but the point is that a segment is congruent to itself, and the reason we know a segment is congruent to itself is because of the reflexive property of congruence. We're going to start using that a ton in this chapter. And since we know that all 3 pairs of sides are congruent to one another, that makes the triangles congruent by SSS, or the side-side-side congruence postulate. Okay, so hopefully that part makes sense to you. 2 things to address. First of all, I essentially wrote a paragraph proof here for my explanation. When it says explain your reasoning, it doesn't necessarily mean a proof, but certainly the proof did explain my reasoning, didn't it? So it might have been a little more than I had to write, but it was sufficient nonetheless. Secondly, you need to understand the reason why I wrote the orders of points in the congruent statements that I did. I said I'd come back and explain this one, and I want to start that explanation with how I made my congruent statement here. Notice that this triangle ABC, if you're going to try to perform some kind of transformation to it to make this triangle over here, it would be a rotation, right? You would have to have a point kind of in the middle of that diagonal, and if you rotated the top triangle around that point, it would match up perfectly with that bottom triangle. For instance, this angle would end up matching up with that angle right there, wouldn't it? And then this angle would match up with that angle over there as well. And so keeping in mind that it's a rotation that would map this triangle onto that triangle, that means that point A here in the top triangle would actually go to point C in the bottom triangle, wouldn't it? So I put A first there, I put C first there. Then B would rotate all the way around until it got to D, so I've got B and D in the same place. And then the C from the top triangle right here would rotate down to become the A of the bottom triangle, and so that's why I have the C and the A like that. Okay, so same thing with this. When I said 7AC is congruent to 7CA, the only reason I switch the order is because A from the top triangle, when you rotate it, becomes C on the bottom triangle. And I just wanted to get the corresponding parts in order. It's a pretty important thing to do. Alright, side, side, side congruence postulate. Still what we're focusing on though. Same directions. Can we prove that this triangle FJG right here is congruent to triangle HJG? And it turns out that the answer is no, and I think you can see why it's no already, but let's start the explanation. Now, even though 7FG is congruent to 7HG because they're both 8 centimeters, and even though 7JG is congruent to itself, that doesn't make these two triangles congruent because the third sides of those triangles, 7FJ and 7HJ, are not congruent to one another. And if not all the sides are congruent, then two triangles cannot be congruent to one another. So our explanation is simply going to be no, because 7FJ is not congruent to 7HJ. Simple, right? Okay, next problem. We're going to look at two triangles on a coordinate plane, and we're going to try to determine, are they congruent to one another? So I've gone ahead and graphed the triangle ABC, and I've graphed the triangle DEF. And we want to use the side-side-side congruence postulate to determine, are those triangles actually congruent, as this congruence statement would suggest that they are? Well, if we're going to show that all three sides here are congruent to all three sides there, we've got to find the length of each side of both triangles. You've got to use the distance formula for that. Now, I'm going to trust the work to you on this, but I'm going to go ahead and write the distances that you get from the distance formula. Maybe show you one example just to refresh your memory. Remember that the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So if you look at the points A and B, if you do x2 minus x1, negative 3 minus negative 6 gives you positive 3. If you do y2 minus y1, 3 minus 0 also gives you positive 3. Then 3 squared is 9, and you have 9 plus 9 is 18. That distance is the square root of 18. And if I apply that formula to all the pairs of sides, these are the measurements that we get. And you can see that I did have one pair of congruent sides between the two triangles. Anyway, segment EF and segment BC, for instance, were congruent. Segments A, B, and DE were close to congruent, but they were not congruent. Segments AC and DF were not really all that close to congruent. I'm looking at the measurements that you see right there. But at any rate, we were able to use the distance formula to determine that the two triangles did not have three pairs of congruent sides. So the triangles are not congruent because the SSS triangle postulate requirements are not met here. So no is the answer. Now, had you had three pairs of distances that were all equal, then you could have said yes, the triangles are congruent by side-side-side congruence postulate. Alright, one more problem that I want to include in this video, and there's only one video on this section, and it's a proof. Yeah, you're excited? I know it. What we're going to do is we're going to prove that triangle JKN, this triangle on the left, is congruent to triangle MKL, the triangle on the right, given two facts, one of which I've marked on the diagram, the other one which, well, wasn't really markable, but we'll go ahead and label something for it anyway. Segment JN is congruent to segment ML, and K is the midpoint of segment JM, and it's the midpoint of segment NL. Alright, now why in the world would that make the two triangles congruent to one another? Well, we already know that one pair of sides are congruent between the two triangles. And then using this whole midpoint fact, alright, if indeed segment K, or point K right here, is the midpoint of segment JM, then that would imply that segment JK is congruent to segment MK, wouldn't it? Because the midpoint divides a segment into two congruent segments. And then by the exact same reasoning, since K is the midpoint of segment NL, that would imply that segment NK is congruent to segment LK, because the midpoint divides the segment into two congruent segments. And so you'd be able to show that the three segments of this triangle are congruent to their corresponding sides on this triangle right there. And so by the SSS Congruence Postulate, the triangles are congruent to one another. Alright, now one more thing I want you to think about is that these two triangles are rotations of one another. If you rotate this triangle around this point, it would give you this triangle, right? Where J would go to M, N would go to L, and K would stay in place. Here's the proof. I'm going to write it in flow proof style. So there's all my given information. Notice I've divided the fact that K is the midpoint of segments J, M, and NL into two separate statements. Didn't have to, but it'll be easier for you to see the conclusions that I make and why I'm making them. Alright, now we don't need to use the fact that segment JN is congruent to segment ML quite yet. That'll come at the end of the proof. But one inference that we made is that since K is the midpoint of segment JM, that segment JK is congruent to segment MK. And I'm going to go ahead and write that now. And that would be based on the definition of a midpoint. Divides a segment into two congruent segments. Now, just pay attention to the order thing again. Remember, if we rotate this triangle around point K to make this triangle, point J would correspond with M. That's why I put J and M in the same places in these congruent statements. Alright, then we also said that K is the midpoint of segment NL, and so that segment NK has to be congruent to segment LK. Also using the definition of a midpoint. Alright, now remember that to show that these two triangles are congruent, we're learning to show that all three pairs of sides for them two triangles are congruent with their corresponding sides. Well, that means it takes all three of these facts right here in order to conclude that the triangles are congruent. So I'm going to draw arrows from each of these three things to my final statement, which is going to be that triangle JKN is congruent to triangle MKL. Like so. And of course, the reason that we're using to justify that those two triangles are congruent is the side-side-side congruence postulate. So there's proving that two triangles are congruent just by showing that they have three pairs of congruent sides. Next video, we'll look at a couple other ways that you can use sets of three measurements to prove that two triangles are congruent to one another. Thanks for your attention. See you next time.